Okay, so today's lecture on numerical integration for 2D and 3D elements with a focus on quadrilaterals and hexahedral elements. Certainly not an exhaustive class of elements to consider. We alluded to the fact that besides quadrilateral elements and hexahedral elements, you could have other shapes. You could have triangles in 2 dimensions. You could have tetrahedra in 3 dimensions, and you can have all kinds of other interesting shapes. But it still suffices to use these conventional quadrilateral and cubic elements. And there's some good reasons for why that is. And it has to do partly with this issue of numerical integration. So we'll discuss how do we generalize some of those numerical integration formulas that we presented in a 1-dimensional context and apply them now in these 2- and 3-dimensional contexts. So before we dive into that, I want to refresh your memory on some of the things that we talked about in the last lecture, specifically regarding how we came up with these relationships between nodal forces, quantities defined at the nodes, explaining how each individual node might discretely displace in different directions independent of one another. And we took that description of displacements at the nodes, and through our formulation of our finite element method, we were able to relate these discrete values of displacement at the nodes to the corresponding values of strain at different interior points within the element. So that was a crucial distinction. Quantities like displacement, at least these discrete values of nodal displacement, we kind of collocate them at the nodal positions. And at the end of the day, what we want are also corresponding resultant forces acting at these same nodal locations. But to get there, we have to go through this sequence of steps. So given nodal displacement, we can relate that nodal displacement to strain by taking the gradient of the displacement field that's been interpolated over the element. And then with this collection of different values of strain evaluated at specific points within the element, which are nominally the integration points. And there may be some variable number of these points at which we might measure and compute discrete values of the strain tensor at each one of those points. And then from that description of strain, we can compute what's the stress at those corresponding points through our constitutive law or our material model. In the simple case of isotropic linear elasticity, that just gives us this direct relationship between stress and strain involving that rank 4 constitutive tensor. And then finally, once we have stress, we can integrate that stress tensor multiplied by the gradient of our finite element shape functions, integrate that over the whole element to come up with the effective resultant nodal forces that act at each one of the different nodes indexed by A. All right, so we have now this sequence of operations that relates displacement to resultant nodal force involving all these different kind of steps that you might want to do in that kind of sequence. And we also, in last lecture, provided some simplified expressions in the case where we assumed a few things. We assumed, first of all, that the deformation of the element is relatively small. So the resulting strain tensor is synonymous with the so-called small strain measure, which is to say that the body doesn't undergo significant deformations, and it's sufficient to assume effectively a linear relationship between those nodal displacements and the resulting strain at each one of the integration points. And if we assume that linear relationship, then it suffices to write out that relationship in the format of this kind of strain displacement matrix or strain displacement operator, which we called B. And we provided explicit expressions for what this B matrix might involve. It's basically just a matrix filled with possibly some 0 entries or otherwise different values of the gradient of the finite element shape functions plugged into different entries. And this gave us a way of taking vectors of nodal displacements at all the nodes to corresponding values of the strain at certain integration points of interest. Then we also had our constitutive relationship. In 2 or 3 dimensions, we could consolidate that constitutive tensor into an equivalent matrix format, a 6x6 matrix in the context of 3-dimensional problems, or a 3x3 matrix in the context of 2-dimensional problems that related the 6 independent components of strain to the 6 independent components of stress in a 3-dimensional case. And then from that description of stress, we could also finally note that that expression in the integrand of this internal force computation actually can be rewritten conveniently as involving this strain displacement operator B just by taking its transpose. So B transpose dotted with the vector of all these resulting stress components turned out to be equivalent to the integrand of that preceding expression we had on the last slide. So we have this sequence of operations, kind of an interpolation slash, also taking a derivative step to relate nodal displacements to strains. We had a stress to strain relationship. And then finally, we had stresses to resultant nodal forces, kind of that full sequence of operations that we wanted to plug in, involving all these different things. And if we combined all these things together into one final expression that gave us a linear relationship between the resulting nodal forces, determined by the deformation experienced by a particular element E, then we can basically compute that resulting set of nodal forces just through this linear relationship involving the element's stiffness matrix, K superscript E, where different interactions between different nodes in the element, sub-indexed by A and B, are determined by precisely these stiffness matrix entries, which can be computed in this fashion, as involving simply B sub A transpose dotted with D, the constitutive modulus matrix, dotted with B sub B. Okay, and integrate that whole thing over the element, and you have your element stiffness matrix. And it actually has certain aspects that probably look familiar to you if you were computing stiffness matrices for one-dimensional elements. It involves some gradients of shape functions organized in sort of this vector or like matrix format, and some kind of set of material properties encapsulated in this matrix. So it's not so different from what we were looking at in one dimension. It's just that now the resulting entries of the stiffness matrix, or rather sub-matrices, are potentially themselves small arrays. So for example, this particular sub-matrix entry case of AB is itself a small 3x3 matrix in the case of a three-dimensional problem, or a 2x2 matrix in a two-dimensional problem. Okay, but now the problem is we have this expression. How do we actually evaluate it? Because now we have to integrate this thing over the whole element. And that's really the thing that we have to deal with in today's lecture. How do we actually evaluate these expressions involving integration over not just a simple one-dimensional line segment, but potentially integrating over some distorted quadrilateral in 2 dimensions or a cube in 3 dimensions? That gets a little bit more complicated. But we'd actually already talked a little bit about how we address some of these issues. We started talking about this when we introduced this concept of the isoparametric mapping, or the isoparametric transformation, which said that any element that we choose to represent, let's say, maybe this kind of 8-node distorted hexahedral element that has nodes arbitrarily positioned and skewed in some configuration, that we can nonetheless relate this element back to some corresponding parametric configuration that is itself a perfect cube with bi-unit dimensions. So a length of 2 on each one of these different sides. And we came up with this relationship that said, I can actually establish also a mapping between discrete points in this parametric domain to corresponding points in this deformed or kind of skewed actual physical coordinates of the element itself. So that was what the isoparametric mapping gave us. And it effectively gave us a way of interpolating the nodal positions themselves. That was kind of the whole concept behind the isoparametric mapping. And it provided us a few useful tools. First, it gave us a way of indeed identifying specific points inside of the element, parameterized by these different xi, eta, and zeta coordinates. And it also gave us a way of determining how did small little chunks of volume get distorted once they went through this kind of parametric transformation. So a small chunk of volume or differential chunk of volume that began as a perfect cube in this kind of parametric domain might be a little bit skewed in this configuration. It would match up in a one-to-one fashion, but the edges of that cube might be a little bit skewed or stretched and things like that. but you could nonetheless figure out what's the relative scaling of that small differential volume by taking effectively the determinant of the resulting Jacobian of this whole transformation. For the details, go back to the preceding lecture on this particular subject. But in any case, we also exploited this isoperimetric transformation in order to carry out a change of variables to figure out how do we transform integration over this distorted element domain, omega superscript E, into corresponding integration over the element's parametric domain, which I'm kind of generically denoting by this square symbol. All right, so if we wanted to actually integrate this expression for the element stiffness matrix, B transpose D times B, which themselves might actually involve some dependence on spatial position within the element. So if I'm evaluating these gradient operator matrices, B sub A and B sub B, really the values that are inside of each one of these matrices involve gradients of the shape functions. And those gradients of the shape functions potentially vary within the element. So we have to include some kind of dependence on position. Additionally, we have this differential volume element that we need to kind of figure out how are we going to replace that. And our change of variables formula gave us a way of dealing with both of those issues. Rather than having dependence on spatial position inside of these expressions, we can just say, well, I can use my isoperimetric transformation to say that I have a mapping between discrete points, capital X, in the element and corresponding parametric coordinates in the element. So I could effectively just say, well, I can express this whole thing as a function of the parametric coordinates rather than the actual physical coordinates, capital X. And then to transform this differential volume element, precisely as I said before, the way that we dealt with that transformation was by noting that the volume scaling of small differential chunks of volume, which I'll call d box or d squared, which is really nothing more than dc, d eta, d zeta, as if I were trying to integrate through this kind of triple integral over this whole kind of cubic domain, that this whole thing can just be replaced by, saying that dB is equal to the determinant of the resulting Jacobian of this isoperimetric transformation, where the Jacobian, recall, was simply just the partial derivative of that, X expression taken with respect to each of the different components of C, eta, and zeta. So the Jacobian gave us this 3x3 matrix, and the determinant of that 3x3 matrix gave us this kind of measure of volume scaling between differential volume elements in the parametric domain versus in the element's actual physical domain. So we could make these replacements, and effectively we get an expression that involves just, dependence on the Jacobian and variable position with respect to parametric coordinates. And now we can carry out our integrals not over this funny distorted domain, but instead over this nice perfect cube. And it's a lot easier to integrate over a nice perfect cube than to integrate over this funny distorted domain. But what's more important than that, certainly we could try to go about analytically integrating things over this nice perfect cubic domain. We could do that, but there's actually some good reasons why we might want to do something different, and specifically why we might want to adopt some kind of numerical integration technique, where even though we've transformed this now to a nice pure perfect cubic domain, it's still beneficial to say, well, let's actually still approximate this integral expression over the parametric domain in terms of some numerical integration scheme, some kind of quadrature scheme, where rather than actually carrying out this integral, we just compute discrete evaluations of this integrand at discrete quadrature point or integration point locations indexed by Q, where I might have some discrete number of integration points that I place strategically throughout the element. And all I have to do is just evaluate these expressions at those corresponding discrete integration point locations, and then sum them up with each of them weighted by these corresponding integration weights, which are kind of like some measure of how much of the chunk of this total perfect cube should be contributing to the overall integral expression. All right, so we have to come up with some kind of integration scheme that can integrate not over one-dimensional line segments, but now can integrate over maybe some kind of square domain or some kind of cubic domain. So to do that, Recall what we did in the case of one dimensions. We came up with these ideal Gaussian integration formulas. These were numerical integration schemes that involved some variable number of integration points. And these integration points were chosen in a very particular way to ensure that we were able to exactly integrate polynomials up to degree 2n minus 1, n being the total number of integration points. So they were optimal in that sense because they were very good at integrating polynomials or functions that can be well approximated by low-order polynomials. So given that our finite element shape functions that we've constructed in 2 and 3 dimensions are also nominally representable as these, finite degree polynomials, as we've constructed them to be these interpolating polynomials, at least defined with respect to the element's parametric space, we should like to use a similar set of these integration formulas, but somehow we want to generalize it into the case of 2 dimensions and 3 dimensions. So how do we do this? Well, suppose we picked one of these different integration formulas. I don't know. Let's just suppose we picked this 2-point integration rule in 1 dimensions. Now, how do you suppose we could go about generalizing our integration formula into a 2-dimensional setting? Maybe I'll illustrate and I'll ask you if this is, let's say, here's the integration domain in 1 dimensions. And if we had integration points positioned here and here in this 1-dimensional context, where should I put some integration points in this 2-dimensional domain that varies over C and eta? Where should I put these?
Same as like that.
Same as this, but also along y. So imagining that if let's say we wanted to integrate some function just along x, we could use this integration formula. But if we positioned integration points here, it would kind of be unbalanced. Another option would be, well, you could put some integration points here and here. How does this look to you? At least then we can integrate with respect to x, we can integrate with respect to y. Do you have other suggestions compared to this?
Like the same distance along x.
Same distance along x and y? Well, let's see. By this, how do you mean?
The distance we have in x, like
Maybe like here? Yeah, okay. Just so I understand. Something like this. Does everyone agree? This looks kind of reasonable?
What if we plug in the x and get the y and let 2 different x in the equation, and then we range on the y-axis for those numbers?
I'm not sure what you mean, but I guess.
If we have an equation of y as a function of x,
Mhm.
then we plug in the x, we get the y, like those numbers in the x-axis, then we range in those y's.
I'm still not quite sure I understand, but I do want to point out that at least what you've suggested here, that this is in fact, I think, the appropriate approach. And in fact, this is the approach that's typically taken to actually carry out these integration formulas in 2D and 3D. And the rationalization is actually quite intuitive. Supposing you had an integration formula you wanted to carry out, it's a 1-dimensional integration formula. So, it certainly applies if I wanted to integrate over just the C coordinate. And maybe this is what you meant. Perhaps this is kind of where we can connect the dots. But if we had some integral involving some function that depends on both C and eta, and we wanted to integrate it both with respect to C and eta, we could do it in basically 2 steps. We could first integrate it over C, and then integrate over eta, almost as if we're carrying out 2 independent 1-dimensional integrations. Is this what you meant? Just to clarify. Well, just as well. Perhaps we can follow up after class if you wanted to continue the discussion. But in any case, because we can do this integration basically first over x and then over y, or rather C and eta, we can basically say, well, over each one of these different coordinate dimensions that we're carrying out these integrals, let's just apply our quadrature formulas for carrying out first integration over c and then integration over eta. So really, it involves this double summation over different integration sub-indices for these different quadrature points ranging over the c coordinate dimension and over the eta coordinate dimension. And if we do that, then what we get is some distribution of integration points that might look something like just what you've described, in fact. So that concept also generalizes to the case of 3 dimensions, where now you could integrate over c, eta, and zeta, and basically just use whatever, discrete number of integration points in 1 dimension and generalize it through a triple integral effectively. So if you had, let's say, 2 integration points in your 1-dimensional integration rule, then it should scale up to 2 times 2 integration points in your corresponding 2-dimensional problem, or 2 times 2 times 2 integration points. So a total of 8 in a 3-dimensional integral. And that's precisely what you get and can visualize in these examples. So the basic idea is you can use these basic 1-dimensional integration rules as we've previously constructed, the same Gaussian integration formulas that we developed previously, and then just define the integration points for this 2-dimensional domain or 3-dimensional domain as the product of all of the integration weights to get the corresponding weights in the 2-dimensional case or a 3-dimensional case. And then the actual coordinates of the c, eta, and possibly zeta components just independently range over those different values as you would have previously defined. So different points in this 2-dimensional domain might range over plus or minus 1 divided by the square root of 3 in that basically 2-point integration rule, where these points were located at minus 1 over root 3 and plus 1 over root 3. So each of these different c and eta components might be plus or minus 1 over root 3, and the same thing applies in 3 dimensions. Now, the integration weights being just the product of these different kind of 1-dimensional integration weights makes good sense. It's kind of like if you're trying to define what's the width of this integration interval in 1 dimension, and then you're multiplying it by the width of the integration dimension in the 2nd dimension. Well, effectively, you could interpret that as being, identifying a small patch, a small 2 by 2 kind of like subset that identifies a small square, which for a bi-unit cube indicates that this small square has just an edge length of 1, an edge length of 1. So 1 by 1 gives us an area of 1 for that particular integration weight associated with basically each one of these different integration points. And the same thing in 3 dimensions. Each one of the integration weights is equal, and it's just equal to 1 octant of this bi-unit cube. So in other words, 1 times 1 times 1 for each one of the different edges. All right. Any questions on some of the basics of how we came up with these integration formulas? No? Reasonably clear? Hopefully. All right. So now the idea is, how do we take all of what we've consolidated from the previous set of lectures to now come to the task of computing element stiffness matrices? And you'll see why this is relevant. Obviously, you're not always going to be concerned with these low-level details, but there are certain details that are worth taking away and being aware of the fact that elements do rely on this numerical integration procedure has several notable beneficial kind of takeaways for you in practical contexts. The first is, it's useful to know that you actually have distinctions between there being, discrete values inside of the element in order to interpret post-processed results. If you're looking at, let's say, some finite element analysis, you run it on a computer using Abacus or ANSYS or whatever preferred software you use. When you visualize the results, oftentimes they present it to you in kind of a nice, colorful way. They usually have like nice interpolated color plots. Sometimes they'll plot just a single value per element. Sometimes they'll interpolate and kind of linearly smear out some of the results. But all of that's post-processing. At the end of the day, they never really show you what's going on in the element. They never tell you that really all they have to work with are these discrete values of stress or strain located at these discrete points within the elements. And it's important to remember that that's effectively what's happening behind the scenes. Because sometimes in the post-processing, they smear out some of those details and it makes it actually a little bit difficult to interpret. Well, did I actually exceed some kind of critical stress state? If they're taking the average value of all these different integration points and presenting you with that averaged value, it might miss something as to what's happening at one of these corner points. It might actually have a more extreme value of stress that might exceed some kind of limit state that you're worried about. So just be aware of that. Knowing that there are integration points in the element is actually a good practical thing to bear in mind. Okay. But regardless, if somehow you found yourself on the other side of these programs, you're kind of trying to program the actual finite element solver itself, so implement some new element type. Effectively, you'd have to program this whole sequence of operations. And it involves, for the purpose of computing element stiffness matrices, actually having to loop over all of the different integration points in the element. And not only loop over the integration points, but also loop over each of the different node sub-indices A and B, ranging over the total number of nodes in this problem. And it involves doing a few things. If I wanted to compute, let's say, the different components or sub-matrices of the element stiffness matrix, ranging over A and B from 1 to the total number of nodes in the element, I first have to loop over each one of these integration points. And then for each one of these integration points sub-indexed by Q, I would have to do that whole sequence of steps that we talked about when we were discussing isoparametric transformations and how that applied to the computation of finite element shape function gradients. Remember what we had to do for that. If you don't remember all the details, I encourage you to go back to the lecture that discussed that. But effectively, what we had to do was this sequence of steps. First, we had to compute what are not the shape function gradients taken with respect to spatial coordinates, x, y, and z. We had to instead compute the gradients of the shape functions evaluated at a particular integration point location and computing the derivatives with respect to c, eta, and zeta, the coordinates with respect to which these shape functions are actually defined. Then we could come and use those shape function gradients taken with respect to the parametric coordinates of the element, and we can compute the Jacobian, also evaluated at some particular integration point within the element. All this is happening just at a single integration point, and you have to do this for basically every integration point. Once we have the Jacobian, we can invert it, and then use that inverted Jacobian to then compute finally the thing we wanted, the actual value of the gradient of the shape functions at still some quadrilateral point location. And given these values of the shape function gradients, we can then plug them into the corresponding expressions for this strain displacement operator, B. All right, we do this for all of the nodes, basically at this same integration point. So I have to compute all these different shape function gradients for each one of the different shape functions. And there will be however many shape functions as I have nodes in the element. So implicitly, there's kind of a loop over, nodes here. Technically, there's a loop over nodes to actually assemble this Jacobian. This is a loop over nodes, and this is kind of a loop over nodes. So I have to determine as many of these B sub A's as I have nodes A. Now I can go back and I can say, loop over the total number of nodes A and B, and then assemble these different contributions to these element stiffness submatrices by actually computing these different contributions using, in fact, those integration formulas that we developed either for 2D or 3D problems. Okay, so that's the whole kind of shebang of how you would assemble finite element stiffness matrices. And there may come a time where you have to execute on this and actually implement this and see how it all comes together. But that'll be probably for homework assignment number 4. So this will be kind of a good reference for that time. All right, but otherwise, I want to ask, again, another somewhat open-ended question. Suppose that I had, let's say, a 4-noded quadrilateral element, and I needed to decide, well, how many integration points should I use in order to carry out that whole procedure that I just showed you by looping over the integration points and assembling different contributions, summing contributions to the stiffness matrix. How many integration points do you think we need to actually do that operation? And before you answer that question, it's probably worth asking, how many integration points did we need in the case of just that single uniaxial one-dimensional element? I hear 2. You say 2? 2 is a good number. I'm going to say yes. I think in the end, it's worth noting that if we're trying to compute the stiffness matrix of the element in a one-dimensional case, it actually turns out that the integrand of those expressions that we were trying to compute involved just a constant expression. So if we were assembling the stiffness matrix for a one-dimensional element, we actually only needed 1 integration point, which was kind of fun. We could get away with that. We probably should have been using 2, maybe, but what do you think? In the case of a 2-dimensional element, which one of these different integration formulas should we use? Should we use just 1? That was fine in 1 dimension. Should we use 4, or do we need more? What do you think? 4 is the minimum. I like that. Any other kind of guesses or supplementary answers?
Five.
You say 5? You say 8. Like maybe, so 5 would be maybe add an extra one here. 8 would be maybe like do everything, but maybe omit the middle one. Or maybe some other kind of funny configuration that's not shown here, or who knows? Well, yeah, it's kind of hard to answer this without actually kind of going through the steps and figuring out, like, what do we actually need out of the stiffness matrix? And could we get away with this? Could we just say, well, we're approximating this integral at the end of the day? And it's all going to be approximate. I mean, certainly there's probably, if we throw enough integration points at it, we're going to converge to the right answer. And that's an important point, that we could theoretically throw an infinite number of integration points at this thing. And as long as it's a consistently defined integration rule, we should still converge to the same answer. So the more integration points we use, we should more accurately evaluate the actual stiffness matrix integral, right? So that's what we hope. We hope that if we use more integration points, then that'll be sufficient to accurately evaluate this actual integral. But what's sufficient for the purpose of just approximating the element stiffness matrix for day-to-day computations? So that's the question we need to answer. How many integration points can we get away with before something bad happens? And we'll have to determine what exactly do we mean by something bad. All right. Well, suppose we took some different sampling of elements, or rather sampling of different integration points, and kind of borrowing from the idea of the 5-point integration formula. We'll actually do sort of a hybrid analysis where we'll look at what happens if we kind of compare a 1-by-1 integration formula, or just a single point integration formula, where there's only 1 integration point we'll put right in the center of the element. And then we'll compare that against maybe the next order up, so a 2-by-2 integration formula, where within each one of these different quadrants, I'll place a different integration point. And then we'll compare what exactly does this element do when we subject it to different deformations. And then we'll see and assess what happens and whether something bad happens. All right, so let's test it out. Let's see what happens when we subject this element to a sequence of different modes of deformation. And certainly there are different ways that we could choose to perturb this element. We could choose to just look at one of these nodes, let's say node number 1. And individually, we could say, let's see what happens if we take just node number 1, fix all the other nodes, and then just displace that node, maybe only in the X direction or only in the Y direction. And we could do this analysis systematically for each of the different 8 degrees of freedom contained in this element, all the X and Y displacements of all 4 nodes, right? So there's a total of 8 different independent degrees of freedom that we can play with in this element. But alternatively, rather than playing with each one of those independent degrees of freedom, individually, we can actually come up with different modes of deformation, which are effectively combinations of deformations happening at different nodes and in different directions simultaneously. And it's useful to look at these modes of deformation because they correspond to rather meaningful physical situations, such as translation, just rigid motion of the element as a whole. So what happens if we take all the nodes and then just all uniformly displace them by the same amount, either in the x direction or the y direction? Now, it should be pretty clear what should happen. All the nodes displace. Tell me, what's the strain at this integration point? Well, even just intuitively, forget about the integration point even. Think about if I had some block, it's translating in space, and if U4x, U3x, all these different displacement components, if they're all equal to one another, then it's basically I'm taking the element and I'm just kind of shifting it to the right. It's not stretching, it's not contorting, it's not doing anything. It's just, translating through space freely. What does that say about kind of the uniform state of strain that might arise in the element as a whole, regardless of what's happening at individual integration points? Yeah, it's just zero. Yeah, so if I have rigid motion, effectively what I should expect is this thing is just going to float off in space. It's not going to stretch at all. And if it's not stretching, it's not going to induce any kind of internal state of, stress or anything like that either. Same thing if I, choose to kick it off into the y direction. It doesn't really matter. In both cases, it'll result in 0 states of strain at all the integration points and 0 states of stress at all the integration points. Now, a little bit more of an interesting case. What if I had a special case where U4 and U1 are maybe kind of opposing the direction of the displacement of U3 and U2? Kind of like we're stretching the element out in this x direction. Now, I've kind of visually shown what happens, but do you suppose that, as I've shown here, that it makes sense that I should get basically the same value of strain and stress at all the different points within this element? Does that make good sense? How would you rationalize that? What's your take on that? Right. So if I have, let's say, these nodes at the left and right of this element, if I choose to stretch them uniformly, let's say in the left and right directions, should I expect that the strain at each one of these integration points should be the same, basically everywhere? Or should it vary as a function of, linear position or things like that? Should be the same. Negative or positive values of strain, you say?
Assuming that for the left would be negative and for the right would be positive.
Well, it turns out that certainly position changes. The relative position of points is different, but it's important to remember what strain is. It's a measure of kind of relative displacement, right? And relative displacement is something like U2 minus U1. That would be the case in our one-dimensional problem. If we were just looking at this bottom edge, like we were looking at a truss element or something that we were kind of stretching axially, we expected to see that the axial strain throughout that kind of whole one-dimensional bar would be just a constant value, right? So it makes sense that if we're doing that, just uniformly at all kind of elevations y through the element, then the resulting strain or axial x strain in this element would be constant throughout the whole thing. It's kind of like we're still looking at this one-dimensional bar element and we're just stretching it in the axial x direction. But now because we have the ability for this element to deform in the y direction too, if we're only displacement in the x direction, then technically speaking, our constitutive model is going to want to say, well, according to Poisson's effect, the element really should want to contract inward this way in order to kind of try to conserve volume in some sense. But if we're preventing it from doing so, we should actually expect there to be some kind of resisting force that's kind of like almost putting these small patches into uniform states of certainly uniaxial tension in the x direction, but also a little bit of transverse stress or plane stress. Kind of interesting. And the same happens if we choose to flip this whole situation and kind of load it now in the y direction. So uniform states of axial strain, or kind of due to this relative change in x displacement or y displacement, result in states of biaxial stress or plane stress that are nonetheless states of strain and stress that are constant throughout each of these different situations. So it's sort of interesting to note that, if I wanted to represent this element undergoing this kind of uniform state of deformation, it appears to me that if we just chose to use this 1-point integration formula, then we're really capturing all there is to know about this problem, right? I could use 4 integration points, but they're all behaving the same. So I could just theoretically just use 1 integration point in this situation, and it should nonetheless capture that overall behavior. The same is true in this kind of vertical case. So that's an important observation. So far, nothing bad has happened in trying to use less integration points, and in particular, just 1 integration point compared to, this 2x2 integration formula. Now, what about shear? What if we took this element and we did something more interesting than maybe what you're used to seeing? What if we took it and we either sheared it along this direction or we sheared it vertically? Now, in this situation, each one of these small integration points will be subjected to some kind of uniform state of shear deformation and a resulting uniform state of shear stress, as evidenced by these kind of like deformed, rhomboidal shapes, and the corresponding arrows indicating the direction of the resulting shear stress acting on each of the different faces of these individual integration points. But here too, in both of these kind of independent cases, the behavior at all the integration points in these pure shear cases is the same. So in this case as well, I could just say, well, 1 integration point is enough. Whether I'm shearing it this way or shearing it that way, it doesn't really matter. So that's kind of fun. So uniform axial extension or, shearing, I can get away with just 1 integration point. And it seems like I'm capturing all there is to really know and represent in terms of the element's deformation. Okay. Now another fun one, rigid rotation. What about this one? It turns out you can actually construct this rigid rotational mode by actually superposing 2 of the different pure shear modes. So if I combine shear in the x direction and shear in the y direction, it turns out combining these 2 gives me precisely this mode where each node is kind of displacing the x and the y potentially, and doing so in a way that basically results in just this pure rigid translation, or rather rigid rotation. And clearly, if we have material that's not doing anything other than purely rigidly rotating, these individual small integration points, the element as a whole, it's not experiencing any relative strain. It's certainly undergoing rotation, but strain doesn't measure rotation, right? It only measures stretching. So technically speaking, there's nothing that resists this motion. It's a purely rigid mode of deformation, which means that the element doesn't feel it. It's just, rotating at a constant rate, and there's no apparent strain or stress that should manifest at any of these integration points. That's an important observation too. So we actually have a few rigid modes of deformation, rigid translation in the x or y directions, rigid rotation, and they all correspond to 0 states of strain and stress in the element. We also have these uniform states of axial extension or uniform shear that result in constant states of stress and strain throughout the element. But the last situation I want to point to is really 2 different situations in which we can play with these nodal deformation in a way where we are trying to emulate sort of a bending mode of deformation, if you like. It's kind of like what you would do to the ends of a beam in order to try to build in some kind of curvature-like deformation. Now, the element can't quite deform like a beam. It can't bubble out like you would with a, actual kind of curved beam under deformation, in part because of the way that we've constructed these linearly interpolating shape functions. They just can't represent that curvature. To do that, you'd actually have to add in an extra node so that it could kind of pop out that direction. But this is as good as these kind of low order 4-node elements can do. Regardless, the interesting result we see is that in each one of these different subquadrants of this kind of I guess, trapezoidal patch, the deformed configuration of this element under bending deformations. Each one of these elements, or rather integration points, is undergoing a different behavior that looks almost like symmetric, reflected about this kind of center axis. Same thing, these are kind of reflected. And some of the components actually change, also going, from below to above this medial axis as well. But the crucial thing to note is this integration point, right in the middle. Right in the middle, the integration point actually doesn't think anything is happening at all. Because of the way that we've defined our shape functions, because of the way that we've defined how we compute, integration point strains, it turns out that a small square of material at the middle of this element, after you subject it to these bending deformations, will remain a perfect square after the element has been kind of distorted in this way, regardless of whether you're kind of doing it in the X direction or in the Y direction. And that's the crucial observation that we see. If we tried to use just one integration point in these situations, what we want is to really capture the reality, which is that the stresses and the strains throughout this element will vary actually linearly through the depth of the element this way, or linearly through the depth of the element that way. But we miss that if we only use one integration point. And that's the problem. So here's the issue. We have all these different modes of deformation that an element can undergo: translation, rotation, stretching, shearing, and bending. And at least for a lot of these, for the translational and rotational modes and the stretching and shear modes, using one integration point is fine. We capture everything we want to know. But in the case of these bending modes of deformation, if we only use one integration point, it seems to the element that nothing is happening. It's a totally unresisted mode of deformation. So if we tried to apply some forces, external forces at each of the nodes of this element, and if I'm only using one integration point, then this element is going to say, well, I'm not seeing anything happening at my nodes. They could be bending arbitrarily, large degrees. And there's nothing that would prevent it from kind of allowing it to do so. Because from that element's perspective, nothing is happening, or at least from this integration point's perspective. So for that reason, something bad certainly happens if we have elements that only have a single integration point and we're trying to subject them to these bending modes of deformation. That's a problem. In contrast, if we used our nice 2x2 integration formula, kind of alluding to your recommendation that really, 4 should be the minimum. That was kind of a crucial observation, and a correct one, I'll point out, that at the end of the day, in order to recognize that we need to resist these bending modes of deformation, we have to include a sufficient number of integration points to be able to kind of sample or feel these bending modes of deformation happening. And that allows us to ensure that the element will remain stable under some kind of arbitrary deformations that might include some kind of combination of all of these happening simultaneously. So that's as much as I think we'll have time for today. But we'll pick up on this subject on Wednesday. Otherwise, feel free to drop by office hours if you have questions on the lecture or on the homework. All right, I'll see you then.